Hello everyone. Thank you for introducing me. My name is Vivek, and today I'm presenting my work on C2 store, which is C2 server profiles at your fingertip. This work has been done with my collaborator Mimon and Shrikant Krishna and my advisor Shrikant Krishnamurthy and Mihalis Palutsos. Yeah, it's good. Yeah. So before we dive into the presentation, I'll just briefly introduce few keywords and definitions. So first one is malware binary, which is a program that runs on a user device and converts it into a bot. And the collection of these bots form a botnet, which is typically controlled by a C2 server, which is command and control servers, which acts as an operational headquarter. So the goal of this project is to basically find the available information about these C2 servers. So the overarching problem statement goes like how to synthesize all available C2 server information. And we utilize an opportunity that there are various sources, but not a single point of reference. So to collect this information, it's not an easy task. There are several challenges. First, there are several scattered and unknown sources of information. And mining information or extracting information, C2 information from these multiple sources have their unique challenges. And we make an assumption here is that we focus on synthesizing existing sources rather than or less on basically doing an active measurement stuff. So why is this an important problem? So first, finding a C2 server or reporting a C2 server can help us safeguarding critical systems and data from cyber attacks. And uh, cyber adversaries are constantly innovating their evading techniques, and no single person or organization can cover all possible C2 evasion tactics. And the community knows it, and they collaborate with each other. They share information like malware binaries, C2 server information on social media platforms, and we leverage that opportunity in this work. Okay, yeah, it's working. And timely detection matters that like spreading the C2 information, like if we know it as early as possible, it will help us to safeguard system. So to this end, we present our work C2 store, which is a definitive capability which collects C2 information from various sources and provides it at a single spot. We overcome various challenges, like we find and identify various untapped sources on GitHub and Twitter. We develop methods to efficiently mine these information, and then we synthesize all the information to create C2 server profiles. To best of our knowledge, the C2 store is the largest database of C2 server profiles, which constitute of basically around 335K C2 server records, spanning across 133 families over last 7 years. So the methodology we adopt is divided into two phases. First is we collect the information. First phase is information collection phase, where we use like 4 unique sources to obtain C2 server information. And the second phase is the synthesis phase, where we combine and synthesize the information with confidence and more metadata. Uh, One of the source is malware binaries, which provides a direct information about C2 server. We did perform static and binary dynamic and network analysis on these binaries, and we extracted a majority of data from these this malware binaries. The details of static and dynamic is greatly explained in our paper. So I would encourage all you to read it. Um, the novel source of information that we use in this paper is particularly from Twitter and GitHub. What we find is community is well aware of basically spreading C2 server information, but it is too distributed to get quickly information, and we build a system to get this thing. But finding information from Twitter is like finding needle in the haystack, and searching for relevant keywords or specific keywords or hashtag may not always give relevant results. So what we did here is we built a network of experts. What we did is like we initially took or manually know like few people who post these informations. we verified their trustworthiness. And what we did is we built a network of expert. And what we did here is we followed an intuition of trusted user follow trusted users, and we built out their social network graph. And the larger bubble shows that like the users that are more connected with each other, and they post similar information. After finding a large number of users, what we started crawling their tweets, we started collecting information what they post on their platform, on their social handle. But we faced a lot of difficulty in processing that data because of language ambiguity containing many abbreviations, jargons, unstructured information. So we utilized ChatGPT and prompt engineering to extract the C2 server information. Once we collect this C2 information from all of these sources, what we did is we collected them at a single place, and we then performed deduplication, filtering, and we started building a complete profile. And by incorporating comprehensive metadata, we added special information such as geographic location and autonomous system that hosted that C2 server, and temporal information such as when it was reported, when it was active, when it was not active, and the family information and network traces. So in case of malware binaries, or maybe in like once we find a C2 server information from Twitter, we started probing that particular server. We started understanding what are the DNS resolution of malware binary made, what are the interaction of bot with their C2 server to get the information about their traces. So once we build this thing, like we wanted to understand what is our scope and evaluation. So what we did here to understand the accuracy is that we evaluate our social mining method. We used virus total as a ground truth. Virus total is a platform which allows users to share IOCs, and there are various antivirus engines that are integrated with it. And we considered a IP address or domain name of a C2 server malicious if it is reported by 5 or more antivirus engines. So what we found is the data, and note that like the virus total also has some delay in incorporating these information. So even if we find it at the first place, the total may mark it malicious. So we periodically probe virus total to basically tell the report about these findings. So overall, after like collecting all of the data, what we found is that Twitter has basically 97% of accuracy, while like when we mine this Twitter and GitHub, and the contribution, when we see the contribution, we found that like 33% of information comes from these social media handles. So uh, the takeaway from this slide is that our social media based method provides significant and correct information. We wanted to understand the timeliness of information. So what we did is on a random day on like 25th March, we took around 600 IP addresses, and that were reported in on Twitter and GitHub, and mined them. And again, we used virus total and threat feed, different threat feeds observed for threat feeds for 4 weeks. And what we found is on even for at the end of first week, only 28% of them were malicious or were incorporated in virus total or other threat feeds, and more than 30% of information was not available for 10 days. And so what takeaway we take from these slides is that our methods find C2 server information much more earlier than it is being reported in de facto platforms like VirusTotal. So we have data, and what we wanted to do is like build a capability which can allow users to basically identify patterns or take some understand behaviors. So we released a open source or basically an online interactive capability. The website is already up at c2store.github.io. And what it provides, it's as user a semantically rich platform. User can choose different sources. You can choose different time, family, or autonomous system, and they can get like different informative visualization and with comprehensive metadata. So to the right, there is a figure or there is a uh, analysis that we wanted to see basically for the red line stealer family, which are the most active regions or autonomous system uh, that are responsible or that are hosting these C2 servers. So so that what we found is Netherlands and Russia are the significant regions where particularly these families are being are hosting this C2 server. Similarly, for like we wanted to conduct special analysis. So again, the same thing. What we wanted to understand is geographical and distribution or autonomous distribution of these servers. And what we found is, like, for example, figure on the left shows that, like, for different families, for Aurora Stealer, BRC4 or Cobalt Strike, different regions are basically uh, responsible for hosting the C2 server. Similarly, the table on the left shows the relation or correlation, like we can correlate, like the Cobalt Strike or is like majorly hosted in Shenzhen Tenzhen AS. So what we understood from this is that C2 server exhibit strong locality. Families, particular family are often clustered at few ASS at a particular region. Similarly, we wanted to understand temporal analysis. What we did here is we considered 1,000 newly reported C2 servers. And what we did is we sent 6 probes a day, like 4 every hour for 7 days. And what we wanted to understand is their response pattern. Uh, and we considered top 5 families: Cobalt Strike, Quarkbat, Mirai, Redline Stealer, and NG Red. And what we found is 95% of these servers do not respond, or only respond to 12% of probes that we have sent. And not and what we understood is that C2 servers does not respond to all probes within a day, so they are not active uh, within a particular time in a day, or they are not basically active every day. So the challenge, this gives a practical challenge that, like, when we want to find live C2 server, when we want to perform active measurement study, we should not be able to basically find or predict any particular pattern for these C2 servers. So the takeaway from this measurement study is that we've understood that C2 servers have elusive patterns with unreliable response patterns. Uh, for behavioral analysis, we found a couple of peculiar behavior. One of them is basically multifamily hosting. And what does that mean is different users or security experts were sharing the similar IP address with different family and different port names. And what that mean is uh, there might be some professionally streamlined C2 server hosting service, which is basically accessible to the attackers, and like you're reusing same system again and again. And to verify this information, what we did is we used once we find this information, we probe it on different ports, and we basically use service banner, showdown queries, or manually inspect the IP address and port number, and we found those were actually active at that time. So this is one of the behavior that we got. And the second behavior that we understood is basically unconventional C2 communication pattern. Uh, so attackers are using benign platforms such as Pastebin. Pastebin is particularly used for text sharing or code sharing. And what attackers are doing is that they embed some Pastebin URL in their code and try to fetch what is written on this website or that particular URL. Now, the implication is the platform is Pastebin is a benign platform, so it will be unlikely to be flagged or marked malicious by any firewall, and the data can go through. So we verified a couple of the URL that we found in uh, pastebin.com, and basically we found that there are basically some malicious exploit code that are being deployed. For example, extracting some information, doing crypto mining, or maybe doing SSH or running SSH brute force. So these kind of commands we found at those URLs, and we notified these things to Pastebin administrator. And what we found is that like after a couple of days, those URL were blocked, and the administrator replied that okay, those were actually malicious. So So to conclude, what we proposed in this work is C2 store, which is basically a number of techniques combined together to collect C2 server information, sanitize them, and combine them with annotating them with rich metadata. So far, we have collected 335K C2 server record, tried to build a comprehensive profile which can be used for different research purposes, which can be used for different security purposes. We build a platform which is basically providing a visual and intuitive information, and we showcase the use case of our platform through some measurement study or some kind of analysis. Uh, and our ambitious goal is to establish C2 Star as a de facto platform when it comes to like when a security community or security expert wants to see a C2 server out there, so they would be able to go to our platform and see those things. So thank you.
Shall I go? I'll go first. Okay, right. So thank you for that talk. Right. So you showed some statistics where you correlated the malware families with the different ASs, right? And showed that there were some on the same ASs. Did you do the same thing on like an IP basis that you could potentially see whether some families are being hosted by the same IPs and potentially being operated by the same actors? Did you observe any of this in your study?
Sorry, can you repeat again?
Whether you observed that any families were being hosted on the same IPs, like by the same servers, rather than just on the same AS.
Right. So in our behavioral study, the first point was actually about a particular IP at the same time. They were hosting multiple C2 families. And this information we got like, so for example, you were posting some family information on social media that this is IP address and it is hosting this family on this particular port, but the other security researcher was posting different information. So we tried to combine this information and we verify it by basically actually sending some probe messages or try to basically manually visiting those websites using sandboxes so that we know actually if there is something hosted. So we did find those kind of things. So a same IP address is basically or same server is basically being utilized for hosting multiple C2 families. And
okay, thank you. And these probes that you sent are basically using the same protocol that the bot families use to communicate with it.
So we have some signatures which basically like for particular family we know like what kind of service banner to send like to or basically request to send to obtain particular service banners.
Okay, thank you. Very interesting.
Oh, great work, interesting results. What was the collection period? I mean, if you go back to, you mentioned like 300,000 malware families, no, 100 malware families. Okay, but the thing is how much you learn from like every week from the feeds. Yeah, like 300,000 C2 servers. And so how much new information you are learning? What's the rate? And have you looked this longitudinally?
So on average, like we were able to collect like 1500 or 200 tweets or like or a C2 server information. But this is collected like from past data as well. So the Twitter API like at that time allowed us to fetch at certain point till certain amount of time. So we were able to collect most of the information from past as well. And then like we were crawling each day and like on average like we were finding maybe 400 or 500 C2 server information that was validated like much later after by virus total or other threat feeds as well.
In your study, you confirmed that the C2 servers are quite dynamic, like they go on and off and dynamic and so on. Yeah, so of course, like a botnets use those strategies to hide themselves. So, you know, what's kind of the value of having IP addresses in that context?
Sorry, can you go?
Right. Okay. I'll give you a different perspective. Once attackers learn about the C2 website and the information that this is providing,
Right.
how will they fight back? Like a kind of you're providing information, like exposing the IP addresses. What's the next step?
So the next step is like right now, I would rate this particular work as a passive measurement, like whatever information is out there, we just collected them. The next approach is to basically based on the locality or some thing that we learned from this work. We wanted to like go beyond doing passive measurement and do some active measurement work. So we'll actively go and ask some of the, so in one of our work, like we utilize malware binary as a gun, and like we try to ask the server, like, do you follow similar protocol? So if it says yes, so we basically uh, treat as a C2 server. So that's what we want to do. Like we want to perform an active measurement study.
So your probes were just pings. You are not trying to emulate the malware family. Your probes.
So the probes are actually basically derived from malware binaries. So we will use those binaries, and like, so even if the attacker shifts from one server to the unknown server that we know, but like if we know some locality reference, we'll just again and like try to scan that particular subnet, and we'll just send the same probes. And if someone responds with like what we are expecting, or elicit some response from the servers that is basically malicious, so once we get this kind of information, we can declare we can find the new live server that is not known by the community.
Awesome. Thank you.
Showed us the results from a traffic point of resident, for example, the majority of servers. Any idea why some countries are more in favor?
So one of the thing that we speculate is basically that these servers are basically, or these attackers are choosing basically the ISPs or basically the cloud service provider that are easy to go in. So, but like we also found that basically the popular choices, for example, we found Amazon, we found Microsoft Azure being basically repeatedly exploited for these purposes. So probably that, but like we have to go more in more detail, like to exactly understand why are these particular countries are chosen often and often.
Okay, then let's thanks to speaker again. Thanks, Vivek.
That works. Yeah, thank you for that introduction. Right, so this is work that I conducted at the Technical University of Darmstadt, which is part of the Athena National Research Center. And is it working? Nope. It only goes forwards, doesn't go backwards. It does. Okay. Yeah. Yeah. All right. Right. So basically, what we wanted to do in this paper is to characterize the current state of how the WebPKI can deal with fraudulent certificates. And by fraudulent certificates, I mean certificates that have been issued by a certificate authority to an unauthorized party for a domain that that they do not control. And this can happen in a few ways, one of which CA compromise is always an option. Another option that previous work has shown, which was kind of the motivation for this work, is hijacking the domain control validation procedure that many CAs use to validate control of a domain to ensure that the person requesting the certificate is authorized to make this request. It's a simple challenge response system. And several works have shown ways, because this is unencrypted communication by necessity, that you can hijack this, or if you can inject basically the proper response into this communication, you can trick the CA into validating your request and issuing a certificate to someone who is unauthorized. So this is basically the situation that we're working with. And this is obviously a problem because attackers can then impersonate the domain that they obtained a certificate for. because these certificates are used by domains to authenticate themselves to clients. And we have a system sort of to deal with this. This is the revocation system. And the process here is that the domain owner, when he finds out about an unauthorized certificate, contacts the CA, lets them know, hey, I did not authorize this certificate, please revoke it. And then the CA does so, and clients can then find out whether a certificate is revoked or not by contacting the CA and looking at the certificate revocation list, or as shown here, using the online certificate status protocol. Right, so this is basically the state up until 2007. And there's one main issue with this is that domain owners still have to find out about certificates that were issued for their domain. So they might not know. And you basically relied on luck. But in 2007, Google introduced certificate transparency, which is basically adds this to the system. And in this system, CAs log all of the certificates that they create in a public CT log. In response, they are sent a signed certificate timestamp. And these SCTs, they basically confirm that this certificate was logged and is then included with the certificate whenever it's presented. It's basically baked into the certificate. And then clients are responsible for validating these SCTs along with the certificate to incentivize CAs to log these certificates. And then all certificates are basically publicly viewable, and anyone interested can query the API of this log and check for their domain name. And if they find a certificate that they did not issue, they can then carry out the revocation. And basically, this monitoring can be done by yourself, or there are by now third-party services which basically provide this service that you can basically register with them, tell them which domain you want to watch, and they will notify you via email if they find something. So this is basically the current state. And we noticed that no one had done a study yet of how effective this actually is, like how performant is this system. And so our first step was to measure this blue circuit, basically. So to find out how long does it take between the issuance of a certificate and the notification, like when can I find out that a certificate was issued? Because since the situation that we're working from is that there exists a fraudulent certificate which is valid, and so we're basically operating under we're basically doing damage control, and so we want to revoke the certificate as quickly as possible. So we want to find out how quickly can we detect it, and so we did some measurements. We basically looked at all of the certificate transparency monitoring options that were available, 15 different monitors. Some of these are tools that you can run locally on your machine. Some of these are services you can register with, and they will notify you. And some of these are like online search services where you can basically use their search function to find all certificates issued for a certain domain. And we registered a few different domains, and with 9 different CAs, we issued certificates, 3 certificates each. And so we had a number of certificates that we tried to detect, and then we basically measured the time it took until we found out with each of these tools that the certificate was issued. And I would summarize this roughly as like most of the certificates that we saw were detected by most of the monitors in like 30 minutes. There's some that work very reliably and very quickly that detect certificates up to 2 minutes after they're issued. That would be like a CertStream, which I would definitely recommend. So between like 2 and 30 minutes is the sort of what we measured for the detection. And then the second step, it would basically be measuring, once we found out about a certificate, measuring how quickly can we revoke it? How long does this process take until the certificate finally shows up as revoked, which would be this red circuit shown here. And so we took those, we did a measurement for this as well. And we took those certificates that we issued. So 3 certificates per CA that we looked at. These were like popular CAs. And basically went through this revocation process. We emailed the CA, let them know that this certificate was unauthorized. Please revoke it. And then typically what they do is they send you another domain control challenge. So like we had to create a DNS text record with a certain value, let them know that we did that. Then they verified that this text record exists and knew that we were authorized to request this revocation. And then the certificate's marked revoked. So this is a bit more sparse. So it's like somewhere between 1 and 15 hours for most of these revocations. Depending on which CA you go to, you can kind of see like the more expensive CAs, like GeoTrust, Global Sign on the left-hand corner. There we have like a smaller spread and like faster revocation, likely because they have a bigger support team, because this is a manual process. And for example, like Let's Encrypt probably has fewer support workers, and there the time's a little longer. Unfortunately, the measurement is a little bit more sparse because each of these data points does come with a price tag depending on which CA you go to. But this is basically, so like 1 to 15 hours is what we measured for the revocation process. So at this point, summarizing the process so far, we basically have an attacker who managed to have a certificate issued, and he can serve this to clients. At this point, the certificate is fully valid. We now know, so it takes about 2 to 30 minutes for the domain owner to find out that the certificate exists, and about 1 to 15 hours to revoke this with the CA. And at this point, the revocation information is then available to clients. And at this point, the story should technically be over, but it occurred to us that the attacker can also extend the lifetime of his certificate a bit by abusing OCSP stapling, which is an alternative to classic OCSP. So classic OCSP is basically client-driven. So if a client is confronted with a certificate when connecting to a server, they create an out-of-band connection to the CA and ask if this certificate is still valid. With OCSP stapling, this is offloaded to the server. So the server periodically contacts the CA, gets the current status, which is signed by the CA, and can cache this response, and then serve this cached response with the certificate in the TLS handshake. And in our attacker scenario, this basically means the OCSP response is under the control of the attacker, and he can basically, while the certificate is still valid, continuously poll the OCSP responder, cache the current response, and as soon as the response changes to revoked, you can use the last valid response and use that in the TLS handshake. And the main problem with this is that the lifetime of these OCSP responses is, for most CAs, 7 days. So 7 out of the 9 CAs that we looked at, the lifetime is 7 days, which means that this can be used to extend the lifetime of the certificate, even if we detect the certificate very quickly and we revoke it very quickly, the attacker can still use the certificate fully valid for 7 days. And at this point, it gets a little worse because we also found out that the vast majority of clients don't even bother checking revocation at all. So even after using this OCSP stapling trick or exploiting this, most clients will still accept the revoked certificate without even checking, which means they would accept it between 90 and 400 days, depending on which CA you go to. And the reason we know this is because we also conducted a measurement for this, which we did with an advertisement network. So we basically took out an ad with an ad net. It's an on-click ad, so whenever this ad is served to clients, if they click on it, they are directed to a URL of our choice. And we basically set the URL to a server that we set up. We set this main landing page up with a valid certificate, so we could measure the baseline requests of clients. And then the client is basically served an HTML file with several image tags, which triggers the browser to attempt to load these images from the specified URLs. And these URLs are set to several subdomains on our server. And yeah, each of these subdomains uses a different certificate. And basically, we log all the requests that come in. So whenever a request is logged in one of these subdomains, that essentially means that the TLS handshake succeeded, which means that the certificate that was being used was accepted by the client. And so this the first subdomain basically just uses a revoked certificate. The second one uses a revoked certificate with a valid stapled OCSP response. And then we also decided to measure the must staple extension. So certificates can be marked as must staple, which means they have to be accompanied by a stapled OCSP response. We want to check how many clients actually check this. And then the last one is a certificate without any SCTs, which means essentially that the certificate is not logged and is not publicly visible. Right, and yeah, basically these were our results. So these percentages are basically the number of requests, or the number of client requests that we received at each of these subdomains divided by the number of baseline requests that we received at the server. So this is a lower bound because the measurement can possibly be incomplete. Like if the user closes our measurement page before all of these requests are completed, then we don't capture that. So this is a lower bound. We did 2 measurements, one in 2022 and one in 23, to have sort of a longitudinal comparison. And for the most part, the results are pretty stable. So the majority of clients don't bother checking revocation at all. So they will just accept a revoked certificate. Slightly more accept it with a valid OCSP response. The reason this is not 100% is probably because not all clients implement OCSP stapling, or because the measurements were incomplete. That's why this is not 100%. Then we also found that a lot of clients don't really care about the must staple extension, which kind of means that the adoption of OCSP stapling is not really being pushed on the client side. And then finally, the biggest difference we saw between the 2 measurements is the acceptance of SCT-less certificates. That basically flipped. So in 2022, if you're a rogue CA, you could essentially create a certificate, not log it in certificate transparency, so keep it hidden essentially, and still exploit almost 3 out of 4 clients. This is no longer the case. This is only like 1/3 of clients do this nowadays. And we kind of looked into this. These are the 2 measurements, 2022 and 2023. And the biggest difference we see if we look at this based on OS and browser is that you can see in the iOS row and the Chrome column that the numbers are a lot lower. So it's mainly Apple and Google kind of pushing this checking of SCTs. Yeah, we also kind of looked at if there are differences in the OSs and browsers in terms of accepting revoked certificates. Here we can see that mostly iOS has gotten better. So since Apple is a little more security focused, they are more strict with revocation checking. But the vast majority of combinations that we observed, yeah, for the most part, don't check revocation. We also kind of looked at this over time. So here you can see the browser and OS versions based on release date, and we can see that there have been, like in newer iOS versions on the right, and in newer Firefox and mobile Safari versions on the left, you can see a decline in acceptance of revoked certificates, whereas on other platforms we don't see that. So these continue to accept revoked certificates. And you might ask yourself, why do clients not bother checking this? This kind of comes back to a different issue, which is soft failing. So these results that I'm showing here are the results of a lab measurement that we did. This is something that previous work has done in 2015, and we repeated this to make sure that this is still valid in 2022 or 2023. And this is basically serving lots of different client combinations a revoked certificate and seeing if they accept it under various conditions. And the main one to look at here is the blocking column. So blocking means that if we don't make certificate status information available, which means for network reasons or whatever reasons, the client cannot get this revocation information, the client will presume that the certificate is valid. And this goes for all popular platforms, which essentially means that under adversarial conditions, if an attacker can affect the network, he can force the acceptance of a revoked certificate because clients will just assume it's correct if they can't get any other information. And if under adversarial conditions you default to accepting a certificate and certificate checking only works in a benign scenario, then some people concluded then revocation checking is kind of pointless. And that's why mostly like platforms like Android and Chrome primarily, but also other platforms don't bother checking at all, which of course again makes it easier for attackers who, even those who cannot affect the network, to just use revoked certificates with clients. Right. So summarize the main takeaways from this study. This is kind of a measurement of end to end to see how revoked certificates are handled in today's ecosystem. And one of the main takeaways is that certificate transparency does work very well. So there are fast monitoring tools that are available. And from our data, we see that there's an increased enforcement of checking of these SCTs, so an increased enforcement of CT. So that's very promising. And from what we gather, administrative revocation with CAs is also quite fast, considering that it's a manual process. So having that done in a few hours is pretty good. One of the smaller issues is that OCSP stapling can be abused to extend certificate lifetime. So if we want to have fast revocation, if we want to detect certificates within a few minutes and revoke them in a few hours, then we should also shorten this OCSP response lifetime so that this is not like a loophole that you can exploit. And the fact that must staple is not really enforced is also something that this is also something that clients should increasingly validate so that OCSP stapling can be more widely adopted. But the main issue that remains to be solved is that clients actually validate this certificate status, because there's no real point in having fast detection and fast revocation if clients kind of ignore the result of this whole process. And since most clients still software fail, this is kind of an availability issue. So we kind of need a system that is resilient and robust enough that clients can rely on access to this information so that they can actually implement hard failing policies. Because if they do hard failing policies now, then these OCSP responders basically become prime targets for DDoSing, and you basically cut off clients from the encrypted internet because no one can access the status of a certificate and therefore can't connect. So in order for this to function, we need a system that can reliably and DDoS resiliently deliver this information. So that remains an open problem, at least until we move to the Scion network. But yeah, that concludes my talk. Thank you.
Thank you very much. So any questions, Oliver? Stars and there, guys. Yeah.
Hi, this is Oliver Gasser from MPI for Informatics. Interesting talk. So as you have pointed out, the whole revocation process is fundamentally flawed, right? So, I mean, Google Chrome, the most used browser, doesn't do any OCSP checks at all. But what instead they claim to use is CRL sets. Did you check whether any of the revoked certificates ended up in CRL sets? And the second kind of more looking forward question is, how do we fix this? Should we simply reduce the lifetimes of certificates even further to, like, I don't know, 7 days, and then revocation will take care of itself?
Okay, yeah, two excellent questions. So the what was the first one?
CRL sets.
Right, CRL sets. So we did do a little investigation that did not end up in the paper because of lack of space, and it didn't contribute that much. But we did do a study of we basically looked through all the CT logs for all the certificates for the Alexa top 1,000,000, and checked how many of these were actually included in these proprietary CRLs. So CRL sets is one. Mozilla also has one, which is one CRL, and Microsoft has another thing. And basically, what we found is that like 0.0001% of even like the top Alexa 1,000,000 are included in these revocation lists, which is kind of by design because they are countering the problem that CRLs are getting too large. So they kind of focus on the most important certificates, which I think also with Google tends to be like intermediate CA certificates, because if those need to be revoked, that has the biggest impact. But so even among the top 10,000, 100,000, top 1,000,000 domains that receive the most traffic, a tiny percent, I think it was only like 1 or 2 certificates that we found that were actually included in these proprietary CRLs. So it's not even an option for like the top domains, let alone the broader internet. And then to address the second question is how to fix this. For me, my read is that it comes basically down to availability of this information, and we can't really rely on CAs to provide this kind of infrastructure that is so resilient that this certificate status is always available. So my current favorite solution is to do DNS to do OCSP over DNS, because DNS has proven to be quite a resilient and robust system. I mean, I don't think anybody remembers the last time the DNS system was DDoSed completely. So, and in the same way that IP addresses are kind of an essential resource to access a domain, the status of a certificate is also kind of in the encrypted internet is an essential resource for accessing a domain. So to me, it makes sense to also deliver this information through DNS, and because of like distributed caching and all of that, it would lessen the impact on OCSP responders and would make this more available, maybe to a point that clients can say, okay, we fully rely on the availability of this information, and if it's not available, I won't connect. So
thank you.
Yeah.
Adrian, good.
It seems, so let's encrypt this, switching to 7 days the time of expiration. So it seems that is happening. And also it seems OCSP is starting to be decommissioned. But actually the observation is OCSP is actually, if done right, would be a good way of doing it, right? So having the website fetch these OCSP responses and requiring them to be stapled is actually a good way. If the website itself cannot even fetch this information, then I think this we can make reliable. And so what are your observations there? Do you think OCSP is not the right way and it should be turned off, or if done right, it would be a good way of doing things?
Yeah, so I suppose you mean OCSP stapling as opposed to plain OCSP.
And done right, right?
Yeah, which is, so OCSP stapling is definitely a better way to do things. There are a number of other advantages. For one, it's faster because you don't need to have an out-of-band connection, and it's also more privacy preserving because the CA doesn't get all these requests from people because they would see which domain you're currently accessing. So it's also the privacy aspect. And it adds another like caching layer to make the whole thing more performant, because then if like you have a lot more clients than you have servers. So if only the servers contact the OCSP responder, that's a lot fewer requests as well. So it's definitely better. I just think that the lifetime should be shortened so that this caching is not so long, which of course also has the impact that the frequency with which servers need to contact the CA to get an updated status increases, right? If they're not if they can't cache them for as long, which then again comes back to increasing the capacity of the system to accommodate this load. But yeah, OCSP stapling is definitely a better option, which is why I'm also surprised that there's so little support for on the client side for this must staple extension, because this is basically a way that a domain owner can force the use of OCSP stapling. So that's something that can be pushed more on the client side. And then I guess servers need to adopt more OCSP stapling. So it's definitely a step in the right direction.
If there's no other question. Oh, okay. So I was wondering also about SCTs, because the way they were intentioned initially was only until the certificate then is included in the logs, the SCT would be used, and thereafter you would use the log proof itself. But then you need to also have a gossiping mechanism so that if you receive an because the attack is if you receive an SCT and then later it's not included in the log, that SCT would then be used to show that the log is incorrect or is malicious in some sense. But this obviously has not, this gossiping protocol has a lot of issues associated with it. And so how do you see that moving forward? CT done right with all these complexities?
Well, I think the as far as I know, the gossiping protocol was sort of intentionally kept separate from the SCTs, because this way it's not, the clients don't have to gossip, but you can sort of gossip separately to ensure the proper operation of the logs. And that, I suppose with the SCTs, it's easier for clients to verify this without creating an additional connection to a log to verify that it's really present. So one is sort of like incentivizing the CAs to log their certificates, because if their certificates are not accepted by clients, that's kind of ruins their business model. And then the other aspect being the gossiping protocol to encourage the logs to operate correctly. So it's two different like incentive structures. I'm not well aware of how much gossiping is being done, like how widely that is distributed or is present. I guess that would definitely be necessary to ensure that the logs operate properly, and that I mean, the main issue is that, or the main thing that this solves is that you don't have another trusted third party. Currently, if you don't gossip, I guess you can still trust the logs, do it on a trust basis that they operate correctly. And in that case, you would still get the benefit of being able to see these certificates and being able to much more quickly revoke certificates. But yeah, obviously this needs to be supported more widely so that you can rely on this system functioning properly.
Yeah, thank you.
So hello everyone, I am Aniket, and today I'll be presenting our work on aggressive internet-wide scanners, network impact, and longitudinal characterization. This work was done during my master's studies at Georgia Tech with my collaborator Jackson from University of Colorado and my advisors Michalis Kilitsis and Alberto Dainotti. I would like to begin this talk by giving you some background about scanning on the internet and network telescope, also known as darknet, followed by the motivation of our study. Scanning is a data collection technique that involves probing public IP addresses to learn about hosts on those IPs. internet scanners could be classified into three categories. First, benign research-oriented scanners that perform scanning, for instance, to learn about security posture of hosts on the internet. Second, internet-wide reconnaissance scanners that scan with the primary purpose of identifying responsive hosts. And third, nefarious scanners such as botnets or worms that who has main aim to identify and exploit vulnerable hosts. Here are some examples of scanners. So the screenshot is from a paper that introduced Census, which is a search engine based on public benign scanning data. And this was designed to help researchers answer some security related questions. Next, on the right, we have another screenshot that from a paper that studied Mirai botnet, which is of course a malicious scanner that scans the internet to identify and exploit vulnerable IoT devices. Now let's see how network telescopes and scanning relate. Network telescope, also known as darknet, is a networking instrumentation for observing and measuring scanning activities on the internet. Network telescope is simply composed of a large chunk of unused but routed IP addresses. And the intuition is that scanners that perform internet-wide scanning will also scan unused IPs of the network telescope, and thus will be visible at network telescope. Note that the term darknet should not be confused with dark web. In our study, we employed Orion Network Telescope, which is maintained by Merit Network to observe internet-wide scanning. Orion tracks scanners, source IPs, packets sent, ports targeted, as well as other network and geographical informations. Note that any traffic that is received on Network Telescope is unsolicited because all the IPs of Network Telescopes are unused, meaning there are no hosts requesting for any legitimate traffic whatsoever. Now here comes the motivation of our study. Despite darknet not requesting any legitimate traffic, we receive billions of unsolicited packets on Orion Network Telescope per day. And we monitor only about 0.01% of all IPv4 addresses. So bigger IP spaces will receive even more of these unsolicited packets. We were curious to know who some of these aggressive or heavy network scanners are and what is their impact on some real networks. This led to our study of aggressive hitters. Aggressive hitters are simply scanners that heavily and persistently probe the internet. In our study, we identified three types of aggressive scanners. First, scanner that probe 10% or more IPs of Orion Network Telescope. Second, leading scanners that send a high volume of packets to our network telescope. And third, leading scanners that scan a large number of ports. However, in this talk, I'll focus just on our first type of aggressive hitters. That is the ones who scan 10% or more IPs of Orion Network Telescope. Note that this definition was also used by Dermerick et al. In their 2014 paper, An Internet-Wide View of Internet-Wide Scanning. We found that scanners that we found from this definition still largely overlaps with the scanners, with the leading scanners based on packet volume. That is our type 2 aggressive hitters. And we refer you to our paper to check out more details about other aggressive hitters. In our study, we provide longitudinal characterization of aggressive hitters on two recent years of data. We hypothesized and later tested that the collective impact of these aggressive hitters on real networks can lead to network performance degradation and can also act as denial of service attacks at certain instances. Now let's see some characteristics of these aggressive hitters. First, we plotted a time series showing count of aggressive hitter IPs versus all the darknet scanner IPs. So in this figure, the gray and the red lines represent the daily count of aggressive hitter IPs, whereas the blue and the black lines represent daily count of all the darknet scanner IPs. The key observation from this figure is that aggressive hitters, which is represented by the gray and the red lines, constitute only a tiny fraction, about 0.1% of all the darknet scanner IPs. The second key observation is that the number of aggressive hitters is increasing with time. Second, we plotted a time series showing the packet sent by aggressive hitter IPs versus all the darknet scanner IPs. And in this figure, the red line represents the packets sent by aggressive hitter IPs. So from this second figure, the key observation is that aggressive hitters are responsible for a majority of all the darknet packets. So despite being only a tiny fraction in their population, they send a majority of packets to our darknet. Now, if we further wanted to look into the subpopulation of aggressive hitters, and in order to do that, we compared our list of aggressive hitters with the list of acknowledged scanners which are essentially scanners that scan without any hostile intent. This list of acknowledged scanners was made available by Michael Collins et al. In their paper Identifying and Differentiating Acknowledged Scanners in Network Traffic. So these acknowledged scanners are mainly researchers, threat intelligence companies such as Census, Stanford University, Shodan. And this table shows the fraction of packets sent by the acknowledged scanners on our darknet. From this table, we can see that at least 1/5 or 20% of the aggressive hitter packets are sent by the non-hostile acknowledged scanners. Now let's look into the impact of these aggressive scanners on some real networks. So in order to perform this measurement, we measured the aggressive hitter packets from sampled net flow data, as well as mirrored packets without any sampling. We performed our network impact measurement on two networks. First, Merit Network, which is a research and educational network based in Michigan, serving over 1 million users. And second, University of Colorado, which is an education network serving over 100,000 users. So in the first analysis, we show a fraction of total packets per day contributed by the aggressive hitters on three biggest border routers of Merit Network, as seen from the sampled net flow data. So in this table, each row represents different days of the week, and the values represent the fraction of aggressive hitter packets seen on the three biggest border routers of Merit Network. The key takeaway from this table is that at least 1 out of every 100 egress or ingress packet that a router processes is a packet originating from aggressive hitter. And this key takeaway is supported by the fact that all the percentages in our table are at least 1% or more. As an example, let's look at the highlighted row, which shows the fraction of aggressive hitter packets on October 1st, 2022. The three routers processes 2.52, 1.86, and 2.59 packets respectively from aggressive hitters. Next, we wanted to analyze the fraction of total packets per day contributed by the acknowledged or seemingly benign aggressive hitters on three biggest border routers of Merit Network. And here we saw that even seemingly benign scanners can create a relatively high toll on networks. And note that this result is from the same day, October 1st, 2022, that I highlighted in the previous table. Finally, we wanted to check the instantaneous fraction of aggressive hitter packets per second on both Merit Network and University of Colorado, as seen from the Merit Network packets, that is without any sampling. The left figure represents the instantaneous fraction of aggressive hitter packets per second in Merit Network, and the right figure represents the same for University of Colorado. The red dots in each figures represent 1 second intervals where the aggressive hitter impact was high. So the key takeaway from these figures is that there are several 1 second intervals where we observe a high instantaneous percentages of aggressive hitter packets, and this can resemble a denial of service attack. Now you may notice that the peaks observed in the left figure is about 12 to 13%, whereas the peaks observed in the right figure is about 2 to 3%. So we figured that the reason for this difference about of an order of magnitude between Merit Network and University of Colorado is due to following two reasons. First, presence of dormant IPs in addition to the darknet IPs inside Merit Network. So these dormant IPs receive scanning traffic, but they don't generate any traffic on their own, resulting in a high fraction of aggressive hitter packets observed. And the second reason is the presence of well-engineered content caches within the Merit Network, which also leads to a high fraction of aggressive hitter packets. So with that, I would like to conclude my talk by summarizing our work. We characterized and studied the network impact of an important subpopulation of internet-wide scanners called aggressive hitters. We found some evidence that the impact of aggressive scanning on networks could be currently underestimated, and therefore we believe that more work is needed to evaluate the aggressive hitter scanning impact on networks other than the academic ones that we studied in our work. And we provide concrete methodologies on how to identify aggressive hitters and provide a quality list of scanners. This quality list can have practical implications where network operators can use this list to block top scanners and minimize the risk of blocking any illegitimate traffic. And finally, our quality list of aggressive hitters can be obtained by requesting at the following two websites. Thank you.
So, any questions upstairs? Is there anything?
Hi, thank you for the very interesting talk. So I have two questions. The first one is, do you have an idea of the comparable sizes of the two networks, so Merit versus UC Boulder, in terms of the IP prefixes or the number of total IPs? Yeah, so a comparison of the sizes of the two networks.
So Merit Network is actually much bigger than University of Colorado. So I don't remember the exact network size, but Merit Network is around like a /13 and University of Colorado is much smaller. It has only 7,000 IPs.
Okay. And my second question is, I think you mentioned that you don't look at IPv6, but do you have any insights into what you might observe in that case?
So good question. We at Merit Network, we do operate like an IPv6 darknet, but we receive very few scanning traffic on IPv6 darknet as compared to IPv4 darknet. And for IPv6 scanning, I don't think like darknet is the great vantage point to observe IPv6 scanning. And instant IPv6 scanning could be like observed from a better vantage point, like a CDN network, which gets lots of IPv6 traffic.
Okay, thank you.
Nithinder from Technical University of Munich. Thank you so much. This was a really good talk. So I also have a two-part question. Number one being, I wanted to understand a little bit more about your acknowledged educational scanners. You used one of the previous data sets, but did you try to correlate it with these open abuse IP databases or any of these where the users are not reporting any abusive data scanning? So did relations with other data sets?
So, no, we didn't directly do any cross relation between acknowledged scanners and other datasets, but we believe like the authors of acknowledged scanners create their list themselves by compiling the data from different researchers and maybe even from scanning reports on different forums. So we just believe the authors of acknowledged scanners that they have done their cross validation of acknowledged scanners.
But is that list active? Like, is it actively updated?
Yeah,
Okay,
yeah,
that's
they do update like a list of acknowledged scanners very frequently on
Okay,
their
great.
GitLab page. Yeah.
Then the second question is, can you give more insights about actually the scanning activity here? So what were the packets that you observed? Over the payload sizes, any other information?
Yeah. So we do provide the profile of number of packets sent on the ports, different ports in our paper. I don't have the results in the slides at the moment, but we do provide like the top ports that are scanned, that are targeted by these aggressive hitters. We do provide the tools that are used by these aggressive hitters, like ZMap or MassScan or any other tool. So we have those details in our paper. Okay.
Any more? Yeah.
Since you are using a darknet, right? I'm not sure this is the best sensor because a scanner typically keeps knocking at your door if you don't reply. And here you don't reply by definition. So this may be overestimating the total traffic that you get because scanners keep getting back to you because you never reply. So this is, if you can comment on this. The other thing I'm not really completely convinced, you say here up to 1% of packets may be a lot and can become even a denial of service attack. But these are SIM messages, right? So these are 60 bytes long. So this is 0.00
Yep.
of the volume
Yep.
the network carries. So also there, I am not totally
Okay.
buying your takeaway message.
Okay, so I'll start by answering your second question. So the 1% or even the 5% impact that we found is the collective impact of all the aggressive hitters. So there are several aggressive hitters that keep scanning continuously our network, and their cumulative impact is 5% or 1%. Yeah, of packets, not bytes, packets. Yeah. And to answer your first question about darknet being a not great vantage point, so we did validate the list of aggressive hitters that we found with gray noise data. Gray noise operates distributed sensors all over the world, and we found a very high overlap, maybe around 99% of the scanners that we found with the gray noise data. So I guess this suggests that these scanners are not only targeting us, but they are internet-wide.
But they target more a darknet because you don't reply. So they target everybody, but once you reply, they stop bugging you. This is what happened, at least normally.
Yeah, so the work I will present today was a collaboration between Technical University of Munich, University of Twente, MPI for Informatics, and University of Münster. So let me start with why are port scans important and where are they used? So with port scans, you can get a rough overview of service deployments on IANA standard ports, for example, or you use them as targets for your application layer scans, which I will talk in a moment. And they are also used, as we just saw, in Census, search engines like Census, Shodan, or by security companies like Rapid7. So systematic distortions from port scans will affect results in all use cases, these and also all other use cases you may have. So let me give you a concrete example. Usually, if we do application layer scans for research purposes, we first use a stateless port scanner like CMAP to scan the routable IPv4 address space. These scanners usually don't have a huge resource impact. On top of these results, we use our stateful, more resource-intensive application layer scans. These use the results of the first scan, and on top of these results, we then perform our evaluations and hopefully write our papers. So this, I want you to keep in mind this example because we will work on this and make some statements based on this workflow. So what are our research questions? And I will also give you a short overview on what I will present to you today in this talk. Our first question is, are there distortions in port scans? And yes, there are. So the distribution of responsive addresses is skewed towards highly responsive prefixes. What that are, we will see in a moment. The second question was, to what extent does this distortion impact port scans? So we see, depending on the port, between 20% and 75% of all responsive addresses in the port scan results are inside such HRPs. We also see different deployment strategies by different ASs. And finally, we also wanted to take a look at the third step. So what impact does this distortion have on our application layer scans? And we see there that we have a lower success rate for targets within HRPs compared to targets outside of these. And the information we gain by scanning additional targets inside HRPs is lower than for targets outside. So let me start with some related work. What did others already do on this topic? For IPv4, we did not find any related work on this topic, but we find indicators that also others see this. For example, by Sikiewicz et al. On their work on the evaluation of application layer services on unknown ports, they state that all addresses within a prefix appear to be responsive, and they also provide reasons why they see this. So we do not investigate this further. So the exact reasons, because they already did that. But what we see, what we also have is in IPv6. In IPv6, we cannot scan the full routable address space, and that's why we have hit lists. And in hit lists, the concept of alias prefixes is already well known. And it's basically an alias prefix is a prefix where each address inside is handled by a single host, and such prefixes induce a huge bias into IPv6 hit lists. In our more recent work on IPv6 hit list, there was a need for a broader definition because CDNs appear to be aliased, but they are not aliased, they are fully responsive. And so you need to apply different considerations for such prefixes, even though they appear from a measurement point the same. We found in IPv4 a need for an even broader definition, and you will see why in a moment. So let me start with, are there distortions in port scans? This is an analysis on TCP 443 port scan, and basically all our analysis on /24 prefixes. And here we have the number of responsive hosts inside a /24 prefix. So there can be from 0 to 256 responsive addresses inside. And what we see is that more than 90% of the prefixes have less than 50 as responsive addresses. But less than 3% have a so-called highly responsive or are highly responsive, meaning that they have more than 9% of addresses which respond inside. If we plot this on an address level, we see that the impact of these less than 3% of prefixes is more than 30% on an address level, so what you actually see in your port scan results. And so this was for just TCP 443. We also evaluate this for a number of ports. This is aggregated for all ports, and what we see also that the extremes are so there is the distribution is strongly influenced by the extremes, and we decided on a threshold of 90% for a prefix to be a highly responsive prefix, to be well below the knee of this graph, because different ports have different behave slightly different, and this is a conservative approach. In our paper, you can also find a comparison with a 95% threshold. So for all following evaluations, we used different data sets, which I will shortly introduce. So first off, we have a weekly TCP 443 port scan from the beginning of 2021 until the end of 2022. We also performed dedicated port scans from Munich and Saarbrücken for 36 additional ports. And we collected or obtained port scans by Rapid7, a security company, which performs their own internet-wide measurements, and where we applied for research access. And there we got 129 TCP port scans and 19 UDP ports. On the application layer side, we use TLS application layer results which base and scans which base on these weekly TCP 443 port scans. And we also use Rapid7, TLS, and HTTP results to complement our 443 scans. And finally, we also use Open Intel DNS data, which helps us to understand the impact from a DNS perspective. So let me continue with our second research question. To what extent do highly responsive prefixes impact port scans? First, here a selection of ports which we analyzed. And what you can see, the impact on different ports is consistently above 30%, except for port 22, so SSH. The ports which are used for IANA standards or which IANA already standardized, they usually have something around 30 to 40% of their addresses being in highly responsive prefixes, while others have a much larger share, and they are usually above 50% and go up to 75%. So when we saw this result, we were interested who deploys this. So where, who deploys such HRPs? And for this, we looked at the AESs. And this is a table ordered by the number of HRPs observed by us over all ports. And the top 2 spots are taken by Akamai with two different ASs. And basically for Akamai, we see around a bit more than 20,000/24s. And nearly all of these are also highly responsive. On in comparison to that, on the 4th rank, we have Amazon, which has a huge number of /24s, but only a small share of it is actually highly responsive. Nevertheless, it's enough for Amazon to be on the 4th rank. Overall, the top 5 cover 64% of all HRPs which we observe. And this basically tells you, in the top 10, we have 4 CDNs, cloud providers, 3 ISPs, and 1 academic network. So, but we wanted to understand where do they deploy this. So we looked at the number of ports where we see at least 1 responsive address and where we also see highly responsive prefixes. And we see there are different deployments. For example, Akamai has only 3 and 5 ports where we actually see highly responsive prefixes. But for at least the second AS, we see prefixes in all evaluated ports. Now, in comparison to this, Cloudflare and Amazon deploy highly responsive prefixes basically on all evaluated ports. Yeah, so we have different deployment strategies, and we saw that the impact of HRPs on our port scan results is significant. So the next step was, what's the impact on our application layer scans, which we do on top of these? And considering the talk before, where we have like aggressive hitters, we were also thinking of what's the impact of doing such scans inside HRPs, which are they responsive, and what does scanning inside help us? So for this, we use TLS handshake results, as I said before, from our local measurements. This includes SNI and non-SNI scans, so including the server name and without server name, and certificate data by Rabbit 7. Rabbit 7 only provides us data for targets with certificates. We also have in our own measurements data for targets which provide TLS service but don't send us back a certificate due to some TLS error. The question we want to answer are how many TLS servers are actually active inside HRPs, and what new information can we learn by scanning such HRPs? So let me start with how many HRPs do actually have at least 1 target which completes a TLS handshake. We see that for port 443, so HTTPS, 84% of HRPs have at least 1 single target inside, but this number is a lot lower for basically all other ports. Here is only a selection. You can find all the data in our paper. This is one responsive target. We then also expanded this to, since you get like 256 responsive addresses from your port scan, how many of these are actually also responsive on your application layer scan? And we find for HTTPS that only half of the prefixes which have at least 1 also are responsive on more than 90% of the targets. These numbers on the other ports, the reduction in percentage-wise is a bit smaller, but in comparison to the initial number of HRPs detected from the original port scan, the number is still very low. To understand what's inside these HRPs, which have such a high application layer responsiveness, we also looked at the identifier. There we used the certificate as a cryptographic unique identifier to see, can we learn something new if we are looking for certificates inside these prefixes. And we find that for HTTPS, only 10% of the remaining HRPs have only a single certificate. So for 10% of the, so for 2,700/24, we only find a single certificate inside this. This number is even higher for other for the mail ports and other TLS ports. So in conclusion, what impact does the application layer does this have on application layer scans? So few HRPs provide actual service on all addresses, as we just saw, and if they provide service, they often tend also to have the same identifier. Notable exceptions here are TCP/80 and 443, but these ports are also dominated by CDNs, and CDNs have different reasons for deploying such have a number of reasons for deploying HRPs. As we all know before, address space is scarce, and they just use their assets. But also Cloudflare, for example, published several blog posts where they explain address agility techniques, which we could verify that these were used inside the HRPs, and TCP proxies on all ports, which also cause HRPs. So we see HRPs cause these distortions also in our application layer scans. And what we propose is, depending on your use case, it could be useful to filter HRPs before doing the application layer scan and scan HRPs selectively and more intelligently. We propose there a DNS and sample-based approach, and we applied this to our data and showed that we still can get 99% of unique certificates while reducing the number of application layer scans by 75%. So this depends obviously on the port scanned, but the reduction of application layer approaches can be quite significant. In conclusion, we defined and outlined what earlier responsive prefixes are. We analyzed these on multiple ports and found 20 to 75% of responsive hosts are affected. We evaluated this on DNS and TLS data. For DNS data, look at the paper. And we proposed a new, more ethical scanning approach. And finally, we also publish our tool to detect HRPs, which can directly plug in your scanning pipeline. And we publish weekly new HRP data for port 80 and 443.
Thank you very much, Patrick. Questions, Marinho, first. Yeah. Yep, works.
Okay, nice work. Maybe you covered this in the paper, but you didn't mention the presentation, unless I missed it. The cause for this high responsive prefixes, are these like network tar pits? You know, like a kind of Alberto, which was in the previous presentation. Like I had a paper about this, about how networks sometimes respond. They pretend to be several machines, but actually it's just a scanning mitigation approach.
So we looked, so tar pits are definitely could be a cause, but they are not the main cause of what we see, at least not what we analyzed. There are different reasons, like CDNs are one, proxies are another. There are maybe also middle boxes, which we did not.
Honeypots?
Sorry?
Perhaps honeypots?
Honey, I would.
Because like, DOD is on the list, right? That's like Department of Defense.
I don't assume that's honeypots because, so usually honeypots in the sense of they provide an application layer service, because usually then there should be at least a TLS handshake. So this is why we don't assume that these are honeypots. There are also DDoS protection services, which do some TCP, which handle basically the TCP the first TCP connection for you. And yeah, there are a number of different reasons. So this is why it's quite complex.
But you did not distinguish in details which type of reasons
No.
did you put? Okay, but future work.
Yes.
Further questions? I mean, then I have a question regarding your vantage points. And you said that application layer vantage scans have been conducted from Saarbrücken and Munich, and you have support scans. But you didn't mention where this vantage point was located.
The port scans?
Yeah, for the port scans.
No, the port scans were located in Munich and Saarbrücken.
Ah, okay.
We used Rapid7 data, which is another vantage point, and we compared also our. So we have also the same ports on from our vantage points and Rapid7, and we also compared our data to a scan in Sydney, where we scanned basically in parallel and showed that there are differences, but they are minimal. So they are usually due to we could show that. In a follow-up scan, you see them from the other vantage point. So these are just flaky networks or network.
Yeah. Matthias, 2 questions in one, if there's time.
Yeah, go ahead.
I mean, you didn't use census. This could be a potential source. And like the second question together is, so is this effect going to be present on census data?
So we didn't use census because we don't have census data, but I assume that it's the same in census data because so at least on port scans, like I said, we used multiple vantage points. We also used Rapid7 data. It's present everywhere, so I assume it's also present on yours or on everyone's side. That's at least from our measurements what we can. So a colleague asked, but I think there was time constraints, like it's. But
any further questions?
So I may add something. What we did is we validated our approach also on, for example, the laser data set, which was published by Isikiewicz, and we showed also that if you scanned outside of HRPs, they had more success, so more application layer success than within each HRPs. So this is maybe another vantage point. So
A quick question: was your work inspired by Li's work? Well, because she discusses a lot. The paper discusses a lot of all bizarre behavior in how machines respond to scans and enumeration, and so that was an inspiration for your work.
So we had the idea for the work before, but then read that paper, and we then came out that it might be a good idea to put more work into it. So we saw this effect before, and then saw that all the others have issues with this effect, and that's so basically